Okay, so finally, we're ready to start. So very much, it's my pleasure to introduce Maurice van Putten, and I've known him for a very long time. In fact, we were grad students at Caltech about 30 years ago. So Maurice did applied mathematics then, and from the very beginning, he started looking deeply into plasma, very large-scale physics, black holes from the very start, Maxwell equations in very different form that is much more intuitive. So after he graduated at Caltech, he went to MIT, where he's on the faculty there, has held several other faculty positions. Now he's in Korea, and he has done some really amazing work at the interface between computational physics and astrophysics. Really, because you all hear about this at this talk, but so a niche between really important discoveries with gravitational waves that can be through data mining of all the data that is available through LIGO, right? This laser interferometry, this gravitational observatory. And then really important discoveries in physics, in astrophysics, through computational techniques. You will tell us about this. So this is perhaps unusual for an INC Chalk Talk, but this provides great synergies. And this is why we have Chalk Talks, so we can really have interactions between the community. Let's probably hear more neuromorphic / neuroscience oriented. Where the same techniques that Maurice is developing can really also benefit neuromorphic engineering and vice versa. In fact, Maurice uses the term synaptic processing in this data mining. So, and I'll leave it there. So Maurice, go for it.
Okay, first of all, thanks to Gert for this opportunity. From a distance, of course, I've been somewhat familiar with UCSD and also this supercomputing center, but it's quite a different thing to be here in person and to give an account of some of our recent work that is directly pertaining to HPC. Of course, HPC is an interesting term because right now it's kind of a generic label for many different types of HPC. And that's partially the topic of my talk. What I would like to emphasize first is, of course, the scale of HPC that may come into play by this particular application of essentially exploring the local universe through gravitational wave emissions. And of course, it's a nice thing to start one's talk with a little advertisement for the James Webb. You might have seen inevitably some of its great images. Partially, I'm highlighting this because much of astronomy, of course, is image-based traditionally. Nowadays, not exclusively. We will talk about time series in a moment. But it also highlights generically, if you're not in astronomy, or maybe you're in HPC or computer science, the kind of things that we do. We like to explore the boundaries of where we are or where we think we are. And like 100 years ago, the idea was there's one galaxy and that's the end of the universe. Now you look at it back and you go like, wow, that was kind of naive. But at the time, that was very serious issue. Now, in terms of extending our boundaries, we would like to go earlier, given that there is a Big Bang, at least there's more than sufficient evidence for it. You can certainly ask, when was the first star born? Literally the first blob of, starting a new nuclear fusion and getting a nice light in the universe. That was the first epoch of reionization. And of course, that's a theoretical question, but it's at the end of the day, it's an observational question. And because James Webb is looking very far in the infrared, it offers an opportunity to readdress this very important question. So a very recent publication in FJ Letter talked about claims of detecting the first star formation at an age of about 5% of the age of the universe today, a few hundred mega years. It's still a bit imprecise because it's a very difficult measurement, but this will continue to play a role in the potentially new contribution by the James Webb. So talking about stars, you know, in the older days, we thought of a star as something that's eternally in the sky. Of course, Galileo first was to break that simple-minded view by showing there's rotation in the sun. And nowadays, we know that the more massive stars actually have a very interesting life. They're born, they have a short lifetime, and then they explode, so-called through supernovae. And what that leaves behind, well, it depends. You know, if there is no explosion, you leave behind a white dwarf. But if it does explode, you leave behind a neutron star or a stellar mass black hole. And you can see examples of this here on the left. That definitely is a neutron star. It's a stellar mass object. Why? Because it's spinning rapidly, and there's a very accurate period of rotation that if you just look at a detailed account of things in terms of energy, spin down, and frequency, you can convince yourself quite strongly that this is a rapidly spinning neutron star. On the right, you see something that through different arguments will tell you that it's most likely a black hole, a stellar mass black hole. It doesn't pulsate because fundamentally for a black hole, your magnetic moment is always perfectly aligned with the spin axis. Whereas this is generically broken for the neutron star. That's why you can see these pulsations. It's not pulsating. It's the beam that is projected on the celestial sphere makes a circle. If you're lucky, you're in this circle. So you see these, you know, bleep, 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 the beam passing by. That is not the case for black holes. That also makes the confirmation of something being a black hole rather than a neutron star sometimes quite challenging. Now, if you look at larger scales, the EHT basically solves this problem by paying a direct visit to these black holes. And so you're not going to be worried about this is a black hole or some hyper ultra-massive neutron star. That issue doesn't come into play here. I'm sure you've seen these fabulous EHT images, which incidentally is also a genuine HPC problem, not only in computation, but also in the size of data. Apparently, they don't use the internet to transport the data. They just carry their hard drives to a shared location for final processing. What I want to highlight here is that it is really at the level of stellar mass objects that you're being confronted with this tricky question. Am I really looking at a neutron star or black hole or vice versa? And electromagnetic observations don't seem to give you a definitive answer when you talk about stellar mass objects. So how would you approach this? Let me first highlight another famous case where this question comes into play. It's a very famous GRB. It was supposed to show as a movie. You can find it on the internet. It's a very nice light curve of a real observation that extends over 10 hours of a GRB 2010-09. And on the left, you see the supernova remnant of the nearby event from 1987A. So both are talking about stellar mass extreme transient events. And both of them pose the same question. You know, is this powered by a neutron star or a black hole? And in neither case do the electromagnetic observations give you a definitive answer. So that's very interesting. It seems to be a fundamental open question in observational astronomy to break the degeneracy between neutron stars and stellar mass black holes. Well, a radically new window then that may provide an answer. Gert, can you take a look at this arrow message? I think it's from my from the second laptop, or maybe it's hidden behind my presentation. Hold on, let me see if I can take care of this. Sorry, let me. I don't know which computer is responsible for this glitch. I think it's from the other computer. Yeah. Okay, this is called a glitch. And actually, it's one of the challenges in gravitational wave observations, because this is a very complex machine with, as you can see from this picture, things you really need to put outside your lab. It's 4 kilometers by 4 kilometers. And the two beams that you're looking at have an angle of 90 degrees in between. because you're looking for spin 2 waves rather than spin 1, if you think about electromagnetic radiation. So you're doing interferometry to look for small phase differences that arise through propagation over 4 kilometers when the propagation is in different directions at an angle of 90 degrees. And so that's very easy to say on paper, but to make it realistic, you need a very complex operation of lasers and mirrors and stabilizations and so on. And of course, if you propagate light over 4 kilometers, even if it is nearly perfect vacuum, you can still be hampered by very, unexpected perturbations, either from the weather or from geophysics, or maybe even an airplane coming by. And occasionally that produces glitches, just like we saw just now. And you need to somehow recognize the glitches and make yourself immune so that it doesn't perturb your confidence in your detection or confidence in your non-detection. And typically these glitches, of course, are detector specific, meaning they happen in one, but not necessarily at the same time in the other. Of course, you should take advantage of that too. It's a bit like, in this case, we saw a glitch and it's in one of the 2 laptops. It's unlikely to be at the same time in both. So that's where data analysis and background analysis comes into play. In the near future, we will have, so I'm showing here 3 detectors that are currently fully observationally operational, although they will be restarted. Right now, they're actually offline because of a upgrade. But in mid this year, the LIGO Virgo and the LIGO H1L1 and the Virgo detector in Italy will be recommissioned and start their 4th observational run. And the Japanese detector, of which I'm a member, KAHRA, is now in the early steps of catching up with LIGO and Virgo. So ultimately, we will have 4 detectors at 4 completely different locations on Earth. And so that will give us perfect opportunities to do localization of sources. So when you think about gravitational waves, how would you summarize this prediction that comes out of the Einstein equations in one slide if you're more oriented towards data analysis rather than talking about the geometry of space and time? So one nice number is c to the 5th over g. That's a fundamental quantity that you get out of the fundamental constants c and g that describes a unit of luminosity. If you say it in terms of ergs, it's something like 3 × 10⁵ ergs per second, but that may not mean very much. You can think about it equivalently as blowing up 200,000 stars like our sun and convert it to radiation through E is mc squared in 1 second. So this number is interesting because this is the unit of gravitational wave luminosity as predicted by Einstein's equations. And that means even if you take a very, very small fraction of this, maybe through some non-axisymmetric perturbation or something else, you might still be looking at a humongous luminosity. And that defines, if you like, the prospect of seeing a lot of things in the universe through gravitational waves. It really goes back to the idea that this quantity is derived from geometry. There's no small parameter. And so even a small fraction is already at the level of the total energy, say, in a supernova. So based on this, you're properly, dedicating your time to explore the different scenarios that might actually break sufficiently axisymmetry and produce gravitational waves that may be observable by LIGO, Virgo, and KAHRA. And in particular, of course, this suggests to go after extreme transient events, their central engines, and especially those that are of stellar mass type, as I alluded to, a supernova, Kokolab supernova, or perhaps the GRB. What we knew previously that was also rewarded the Nobel Prize, the whole stellar binary, that had a luminosity, or still has today, because the system will live for another few 100 million years, of 10 to the minus 28 times this quantity. That's roughly 0.15% of the luminosity of the sun, but then in gravitational waves. You can't observe this directly, but you can see the residual significance in defining the evolution of this binary. It's losing energy. So what do binaries do? They contract by the virial theorem. So they spin up. So you should be able to see a shortening of the orbital period of that binary. And that's exactly what they observed. And it's really in remarkable agreement with the predictions of general relativity. So we went from 10 to the minus 28 to something much more dramatic, which is shown here, 0.1% of L0 in this first, dramatic, fortunate detection of two relatively high mass, stellar mass black holes that were merging and coalescing into one black hole. So this was a tremendously powerful event that emitted on a timescale of much less than 1 second about a few solar mass in MC squared in gravitational waves. So that was successfully picked up by LIGO in 2015. And then crucially, if you ask, how is LIGO designed to make a confident detection? The principal part is you have 2 detectors. And now we have 3 with Virgo, and tomorrow we will have 4 with Cathra. One detector obviously is not enough to look for something new, even if you're trying to confirm something that you have some ideas about. You need to have completely, physically, statistically, independently operating machines that then should give you the same message that you pick out from the sky. So what you see here in particular is an ascending chirp, as you can see. In the lower panels are spectrograms, and you see this ramp up. This is basically a dramatization, but then in real space, of the whole stellar binary. They emit a lot of energy. They increasingly emit more energy at higher luminosity, so they contract faster and faster until, of course, they meet and they merge into one object. So it's a positive chirp in that technical sense. And interestingly, the peak luminosity is about 0.1% L0. And you can argue that that's pretty much what you would, not so much what you would expect, but that's pretty much the maximum you would expect from black hole mergers. It's in that sense, the 0.1%, if you average out spin effects and those kind of things, it's in its own right a fundamental number to keep in mind that may actually be useful in future surveys when you start averaging these events. Now we have, in the last effectively 6-7 years, we have many more such detections. And so we are gradually building what some people call a graveyard of stellar remnants, namely those black holes that appear in binaries and they merge on these timescales that we can actually observe them. And then, of course, an interesting question is, when did they first form? What is their parent? The parents are massive stars. But good luck asking a black hole, when were you born? Because there's classically no memory in the black hole that tells you how old is the black hole. So you have to use an astronomical argument. And recently, as a graduate student project, we published one paper on this by falling back to the fundamental so-called salpeter initial mass function. And then you can argue that they actually must have formed somewhat recently. They're not from the early universe like James Webb is now highlighting, but rather from relatively low redshift. Now, in the left bottom here, you can see, if you like, outliers to this survey in terms of much lower mass. And they also use a nice orange color here to emphasize that there you're looking at neutron stars, not black holes. And if you look at all the way to the left, that binary with 2 neutron stars, you have to look a little bit closely, but then you see that the dot produced has 2 colors, blue and red, expressing the uncertainty whether the product is a neutron star or a black hole. Just like the remnant of 1987A, the supernova nearby in the LMC. And then you go, you're confronted with the same question once again. So what really is it? Obviously, it's going to be one or the other, but what kind of observational diagnostics are you going to put in place to decide whether it's a black hole or a neutron star? Interestingly, you can extend the same question to even questioning whether the precursor, the binary itself, was it really a double neutron star system, or perhaps with a small probability of neutron star black hole? Most of us comfortably believe it's a double neutron star system, but as an observational challenge, what makes you feel so confident about it? That's an interesting question. How would you quantify your confidence level that it really is double neutron star and not neutron star black hole? So we'll come back to that later in this talk. So a artistic summary, well, on the left actually is artistic, on the right it's also an artistic, but what is sketched here by labels is actually what happened. Namely, on the left, an image created to dramatize the merger of 2 neutron stars in this 0817 event, and on the right, the associated kilonova that represents an outflow of a very rich wind of neutrons that then are responsible or given a scenario for an R process making the heaviest elements that we have in our periodic table. So if you wonder where does your gold come from, it actually comes largely from events like this. Perhaps not uniquely, but this is definitely a major contributor to the production of heavy elements, including gold. It's just too bad this is at 40 megaparsec. They produced this one produced roughly a few hundred times Earth mass in gold. Obviously, this is something that people exploited by reaching out to all the newspapers and news media because it's a highlight of this particular event. But on the gravitational wave side, what it took was the merger of two neutron stars through the energetic loss in gravitational waves. And again, the question, as I just alluded to, is still, what are we looking at, a neutron star or a black hole? So now I will introduce a bit of housekeeping. If you take up this question, you should be at least, consistent with some very basic notions of how physics operates, which is subject, to be sure, to energy conservation. If you put something in and then you ask what comes out, even though it's a black box, it should not be that you get more energy out than you get in, right? That's very basic. So what you put in is the best estimate from the merger chirp that LIGO provided. It's a little bit tricky because what you measure is the so-called chirp mass. It's a combination of M1 and M2. You do not directly see M1 and M2, but through careful match filtering, you can still get a decent estimate of this, but the uncertainty is certainly more broad than for the chirp mass itself, but it's about 2.7 solar mass. And so that's the energy that you put into this event, up initio. And then you ask, what kind of emissions may I expect? Other than the kilonova, maybe there's a GRB, as I'll point out in a second, maybe there's some additional gravitational waves. Obviously, whatever you produce in radiation should be less or equal than this total mass minus the mass energy in the remnant. And of course, the mass energy in the remnant, okay, if it's 0, it's unlikely, but that will give you an absolute limit then of 2.7 solar mass mc squared in anything you might conceivably produce in radiation coming out. And so the allowed region in your searches for anything like gravitational waves should be bounded a priori above by 2.7. Now, at the same time, then you should keep an open mind as to what this might conceivably be. Maybe it's an ascending chirp, maybe it's a descending chirp, maybe it just fluctuates, who knows, right? So really, the approach we took was something like this, a complete open-minded view as to what might be produced in gravitational waves following this merger. And in particular, the only constraint, or if you like, the only focus we give is that it should be a transient. We don't necessarily expect all of a sudden a perfectly monochromatic signal coming out of this event. And that's important because if you look at, and I'll show this in a second, look at LIGO data, then there are many lines, so-called violin modes from the detector. So they can be safely removed when you're looking for transient signals following this merger. So to keep an open mind, we follow this approach. Obviously, there will be some frequency or maybe multiple frequencies to anything that might come out, but because it's going to be a transient, there will also be a finite DFDT. Normally, when you do a typical analysis and you use FFT, you're actually doing match filtering over constant frequencies. So here we take it explicitly that we're going to densely cover the frequency space that you think may be relevant, but including a dense coverage of DFDT. And we exclude DFDT equal to 0. So that makes, of course, this calculation a bit expensive because the usual resolution you use in F, you're now going to apply also to the FDT. And we also insist that we have symmetry for anything that goes up in frequency or goes down. And that's easy to do. You just make sure whatever templates you use, you time symmetrize them. So you reverse them and then you just add them. So by construction, sensitivity to descending branches will be equal to sensitivity to ascending branches. And the way graphically, you can think of this as indicated here by these green butterflies. If you look at this as a frequency as a function of time, then you fill in this plane with these green triangles, meaning that any trajectory that passes through the green will be successfully put to the output, and anything that's horizontal will be suppressed. because the DFDT then will be 0. So if you like, the green indicates location of frequency and finite DFDT that defines this pass filter. So it's going to be dense in F, it's going to be dense in DFDT, and of course, at the end of the day, you want to do some parameter estimation. And to do this maximally, you should extract a PDF with sufficient sampling, maybe 100 samples. So whatever you do in your F and DFDT, just multiply it by 100, because you're going to need a full, properly sampled PDF. And as I just mentioned, we explicitly avoid DFDT is equal to 0. If you are interested in this, you can just use plain vanilla FFT. There's no need to do all of this. Okay, so this is what you would get if you take LIGO detector data, vertically as frequency, horizontally as time. This is from an older data set. You can see these lines in the data in your spectrogram. That's provided by the detector. Each line represents a violin mode because there are wires that are suspending the mirrors. This is not a detector in space, so you need to hang up your mirrors somehow, and any wire will create one or more violin modes. That's inevitable. People pay a lot of attention to the quality of the wires so that there's least dissipation and so on. So they will be very thin, but they will in amplitude be very pronounced. So you're not interested in those if you look for transient signals. And as you can see on the right, all of this is very successfully suppressed. You get a very nice smooth background in noise. And of course, the quality of the noise effectively defines the quality of your sensitivity. Okay, so why is this expensive? Well, as I mentioned already, it's not just dense in F, it's dense in DFDT, and then you have to repeat it many, many times in your ultimate parameter estimation. So if you apply this to, say, 32-second segments, so imagine you're doing your correlations between data and templates over 32 seconds, so that's 2 to the 17 samples, and say you start with a snippet of data that's 2,048 seconds, you very quickly go to a few times, actually 10 to the 19 flops. So that's the minimum requirement that you need to be able to handle. And you're probably not going to do this in 1 second. I think it's kind of like now the world standard. I mean, the maximum exaflop. When they say exaflop supercomputer, they mean exaflop per second. Here, I just mean exaflop in total because I need several weeks to do this. But it gives you the scale. And of course, it also gives you a motivation to think, how can we speed this up in order to be a little bit more real time as say new observational runs like 04 will start to commence later this year. One of the, when you do an exaflop calculation, you want to have some level of heterogeneous computing. You need to develop your nodes and your networking to operate the nodes with sufficient load balancing. And so here's an example. I was kind of curious as to what you would get out of, a fairly heavy quad node GPU system. And of course, you want to use HBM2 because for FFT, it's bandwidth limited on a GPU. Unfortunately, you have to tunnel through the global memory to do your FFT when FFT is greater than 2 to the power 12. So what I was able to experiment with is ultimately what is feasible within current commercially available technology is about 200 kilohertz correlations between 2 to the 17 sample data chunks and 2 to the 17 sample templates. And then you're running at about 1,500 watts. So that's a very useful point of reference if you think about, what can my next machine do, for instance. And all of this, of course, has a hidden scaling, like when you only get to the 200 kilohertz if you do maximal data and so on, so that all the GPUs are sufficiently busy. And I also added here a little Zenodo piece of software that I often use in my own, quick benchmarking to see what kind of GPU do I have at hand. And it will simply make this kind of a graph that shows the performance in gigaflops as a function of FFT size. So, but one node is not enough. It's not necessarily because of this 200 kilohertz, but for many other reasons. So you would like to have a fully scalable setup because you never know what comes tomorrow. You'd certainly we are hopeful that 04 will give a lot more events to analyze. Yes?
So in this scheme, I mean, you're relying, of course, pretty heavily on having that bank of templates, and you reliably simulate those with respect or whatever, right? If you're looking for a burst signature, I don't think we have a bank of templates because we don't really know.
Yeah, you want a model independent, a model agnostic bank of templates.
Yeah, and
right? That's what we did.
Yeah.
So we choose a intermediate. So there's one key which so it's a very good point. One key search parameter is that the intermediate time scale of phase coherence. That's the starting point, which you don't know is a search parameter.
Well, there could be different scales.
And it could be correct.
My question was really is that let's say that you hypothetically made such a bank of templates. Would the rest of this, flow for analysis be roughly the same?
Yeah. Technically, it's the same. Yeah. That's right. I mean, the way I set it up is one reason I felt it's okay it's a bit of effort to set this all up. And you ask, why am I doing this? Only for this event or exactly like this? Is it more general? But then if you think about it, also talking with Gert, the idea of doing a correlation, that is so incredibly universal. It's not totally not restricted to astronomy. So to have an A and a B and then create a C out of A cross B, right? So that's how I set it up, very general. Including scalability, yeah? So
just to clarify, so is this like an unsupervised bank versus like a curated set of wavelets or kind of signals that you're comparing against?
No, the bank is model agnostic by allowing for, as I said, as a search parameter, intermediate time scale of phase coherence. We chose half a second. Maybe for other signals, you might choose 1 second, 10 seconds. But for this event, I'll show in a moment, half a second gives a good result. And then on that time scale, you say, let's do a Taylor series expansion of my signal, meaning you have an F and a DFDT. Of course, you don't know F, you don't know DFDT. So you just take a very dense bank covering that unknown. And then you time symmetrize because you don't know whether, what might be happening, whether it goes up in frequency or goes down. So that's model agnostic, right?
Okay, interesting. Yeah.
Within a certain window, of course, of, I don't go to a megahertz. I go to, in this case, 700 hertz, essentially from zero. Zero actually excluded, but say tens of hertz to 700 hertz. And then with a finite range of the FDT, which will be, say, motivated by a few hundred hertz change in frequency over a few seconds. So roughly on the order of, but I cover a whole range of, say, 100 hertz per second slew rate. And that's how you do it. You define a frame, basically a field of view in parameter space, and you take a look. So one of the things, because of all these uncertainties, is you would like to be scalable. Maybe tomorrow you need to do 10 times more work calculation-wise. And so what we developed is something that also takes care of a real-world situation. If you look in your own labs, you probably find you have many, computers. The latest is probably the greatest, but then you have some other computers that are still completely fine, but they're not as powerful as others. So you have a heterogeneous set of computing hardware. We are not in a position to always buy what they call in MPI language a homogeneous universe, new rack of nodes. So you would like to make sure that you have nevertheless proper dynamical load balancing if you're doing a process that comprises many, many tasks. And each task, for instance, may be related to one sample of extracting your PDF. So there's usually, in this case, a very natural partitioning of an entire process, an entire analysis into smaller tasks. So the way we implemented it in BASH for portability is to have basically a shopping list of tasks. It can be very small, it can be very large. The largest one I used was like 1,500 items. And then you allow each node, which can be in a single LAN or multiple LANs that together make a wide area network, to access that task list one by one. So you need to make sure it has atomic access, because you don't want to distribute one job to two nodes. That would be kind of silly. So if the tasks are sufficiently small, that means as a result, then essentially all the nodes will be busy all the time. You know, as soon as they're done, they will request a new line item from the list. So this is very different from the usual MPI, where there is a server that basically issues tasks to nodes, right? This is the reverse, where nodes are requesting, you know, I'm idle, give me something to do. So that works very well. As I was alluding to, the key astronomical question is, what did we look at here in terms of the remnant, neutron star or black hole? And one hint you get from the associated GRB. There is a very nice GRB associated with this, so-called GRB 1708-17A, and it lasted about 2.9 seconds with an uncertainty of about 0.3. It's a very non-trivial spectrum, as you can see already from this colorful plot. But the key point here is that it appeared delayed by about 1.7 seconds. That is a huge time scale, because the dynamical time scale of these mergers is tens of milliseconds. Okay, so this is a very anomalous time scale that really poses a fundamental question. What happened? And that may be related then to this very question: is the remnant a neutron star or black hole? So our analysis gave this spectrogram. So we captured the merger chirp that you expect from any type of these compact binary coalescences. And in the lower panel, you see the light curve of the GRB. That's basically photon count in gamma rays. And then it's interesting also to highlight then the gap of 1.7 seconds and the 2.9 second duration of the GRB. So that's roughly a total of, you know, 4 or 5 seconds that I'm adding here below. And then if we do our analysis, we find that there is a continuation of the signal. But remember that the technique we use by construction is time symmetric. So if it picks up something going down, it will be for the exact same reason that we picked up the merger signal. So this is an interesting challenge then to ask, how would you quantify the significance of this feature? And LIGO agrees that we are apparently looking at something more sensitive than their pipelines. But of course, at the end of the day, the homework is the same. How do you quantify the significance now of a potentially positive identification? So there are a couple of things you have to do. Apart from the statistics, you would like to get a handle on the energy. You know, what energy did this actually represent? So the unit I'll be using is percentages of a solar mass mc squared. That just means through the E is mc squared formula, take 1% of the sun in mass and multiply by c squared. So that's my unit. Now the merger signal was known to produce in the observed range from 0 to 300 hertz, about 2.25%, and up to the expected true evolution to 600 hertz, it would be something like 2.5. So you were thinking about something at the level of a few percent that is a natural scale in this problem. Of course, the only way you can determine the energy is by doing some benchmarking, some calibration. You have to do this in any such pipeline. So we scanned over a 2-parameter range of injections, obviously using different energies from 0% to roughly 8%, and also different time scales of decay. You know, it's a descending feature, and it's a log plot, semi-log y. So try to fit it by a descending, exponentially descending feature, and that has 4 parameters, which is incidentally also an issue a topic you might want to look at using machine learning these days. You're just doing image analysis and try to extract some suitable parameters that would make this quantitative. So the energy then, based on this extensive calibration, based on 56 injections, is 3.5 plus or minus 1% m solar c squared. So it's a little bit more than in a merger signal. And the time scale of decay, we estimate is 3.0 plus or minus 0.1, which is remarkable because the duration of the GRB was 2.9 plus or minus 0.3. And actually, you could already sort of get a feeling here too that the signal seems to terminate exactly when the GRB terminates, which of course is what you would expect if they share the same central engine. So what does this 3.5% mean? So here is, if you like, the opportunity to finally break the degeneracy concerning this question. There are other arguments, but I'm highlighting here the energy argument. So the 3.5%, you can argue, based on this so-called quadrupole gravitational wave formula, for which, in essence, has already been awarded the Nobel Prize to Wilson Taylor. If you take into account the fact that what we observe is less than 700 hertz, that means that the spin frequency through the quadrupole radiation formula is less or equal than 350, that if this were to be a hypermassive neutron star, its rotational energy would fall short by at least a factor of 4. So a neutron star simply is not powerful enough to create this kind of output. And that's illustrative, if you like, for this idea that it's not an exaggeration to say that the gravitational wave observational window is really quite radical. It can do things you cannot do in the E&M window. All right, so what about then levels of confidence? So here is, if you like, a mixture of statistics and HPC. You need to make this quantitative in terms of, what's the probability all of this is just happening by chance, popping out of the noise. And there are several arguments that here come into play. The first is by using a astrophysical argument, namely, you would expect the central engine to be born before the GRB. That sounds reasonable. And that the central engine is born after the merger. So you would expect the start time of this gravitational wave signature that represents the activity of the central engine to be somewhere within this 1.7 second gap. And depending then on your total duration of analysis, in this case, 2048 seconds, if indeed TS with a sufficiently small STD, uncertainty in your measurement, is within this gap, then you immediately have a false alarm probability of 1.7 divided by your duration, 2048. Okay, so this is what we get. And here you see a PDF that indeed contains 99 elements that represents the full estimate of the start time. It falls very nicely within the 1.7 second gap. And because we get a full PDF, we can substantially talk about the uncertainty. If you just go by the STD, and of course here we don't normalize by the number of data points inside, because all of this is generated just by getting a feeling for the effect of noise. These are not independent observations. We only have one observation. So this is the bare bones STD, not STD divided by square root of n. We get 0.92 plus or minus 0.08. So that's well within the gap. And that should be compared with an estimated lifetime of the hypermassive neutron star believed to be responsible for all this gold coming out. They estimated 0.98 plus or minus 0.3. So there are two actually issues, there are three issues here that are interesting to mention. Firstly, they are statistically consistent. Secondly, the uncertainty in gravitational waves is better. That's actually turns out to be true throughout this calculation than E&M. It's not so surprising because uncertainties in gamma ray astronomy are always, well, fortunately, we can resolve many things, but they are never as good as you get from lower energies because you just don't get too many photons at these very high energies. And then lastly, you might consider perhaps the 0.98 is indeed a little higher than 0.92. Obviously, they're statistically consistent. We're talking half a sigma issue or something like that. But it is not inconceivable that this might actually be true. And that has to do with what is the true source of the kilonova. Is it only the hypermassive neutron star, or maybe there's a little bit of contribution of a lot of neutrons coming out from the central engine, the black hole and the surrounding neutron-rich torus that came afterwards? So that's an interesting open question. So how do we then maximize our level of confidence in this analysis? So the beauty of having two detectors is that you have two ab initio under the null hypothesis, statistically independent observations. And so far, I just showed you the spectrogram that is actually a merged spectrogram, essentially combining the two streams through these images, spectrograms, which effectively acts like an average. But of course, complementary to an average is a difference. And formally, that's a unitary transformation through a rotation over pi over 4. And that kind of unitarity assures you that the mean and the difference are, under the null hypothesis applied to H1 and L1, are also statistically independent. So whatever you do in terms of PFA on the mean, and supposedly you can do something interesting on the difference, you can then combine them through that product, in particular because the first is an ordinary probability in the sense of Blaise-Pascal. It's not a p-value. The second one may or may not be a p-value, depending on how you look at it. But obviously, ordinary probabilities are can be happily multiplied with anything else. You don't have to use correction formulas there. Okay, so here's the result if you just look at H1. So this is really a direct observation with no further processing. And here you see the result for L1. So now it's a little bit harder to see, obviously, because this is really looking at slightly more noisy spectrograms. But what is important is that the image analysis nicely picks up the results and parameterizes the start time and the characteristic time scale of decay. It also actually registers the start frequency and the final frequency, but that you cannot put out because there will be too much data. So that's maximized over in the, if you like, post-callback function before you write things to the disk. So now imagine you're repeating this exercise with, say, slightly different template banks, and perhaps applying a stride before you apply this to the image analysis. So, and then you can extract a PDF for each. So we did that using effectively 320 samples of each PDF. And here you see the result. In blue, you have the PDF for H1. It's a little bit more powerful, as you can see, than the red, if you look at the right panel, rotated over 90 degrees, because L1 was a little bit less sensitive in the higher frequency regime. And then you can do a cross correlation. So rather than asking is, the start time in one detector consistent with the start time of the signal in the other detector, we simply ask, are the two PDFs consistent? Because that's a more proper way of making a comparison. And so, yes, what do we find? We find that if I cross-correlate these, that the maximum of the cross-correlation happens exactly at delta t is 0. So that's simply a consistency check, right? It has no context. It doesn't care about the precursor merger signal. It doesn't care about the GRB. It's just, supposedly these two detectors are picking up the same signal, the same message, and that message, when parameterized, should be entirely consistent. So this is statistically independent because it's essentially looking at a difference between the two. And so you can just consider the combination of these two PFAs. So we have a 1.7 divided by 2048. We then have, given the uncertainty in our second analysis, 0.1 divided by 2048. And if you combine this, we get a total product of 4.1 times 10 to the minus 8. That's a z-score of 5.5. So that is more than the 5 sigma that is normally required to talk about a detection or an observation. Okay, so what's the story then we have so far? We start with a merger that was actually driven by a loss of energy of about 2.5% m solar c squared, and that's responsible for the ascending branch. But the story continues. You then form, indeed, for slightly less than 1 second, you form a hypermassive neutron star. It may have produced gravitational wave emission too, of course, but actually from numerical simulations and many other considerations, if any, those frequencies will be very high, a few kilohertz. So that's outside the range of LIGO so far. At any rate, based on two entirely independent analyses, the analysis of people studying kilonova, so basically electromagnetic data, you estimate the lifetime of this hypermassive neutron star state is less than 1 second, and we get the same based on the start time of the ensuing gravitational wave emission. But what is interesting through this gravitational collapse that then signifies the end of the life of the hypermassive neutron star is that you are, of course, also gaining some rotational energy by the ballerina effect, because collapse to a black hole makes the object smaller, right? So the moment of inertia is smaller, and so the rotational energy goes up. So you gain by a factor of a few, and the resultant is a rapidly rotating black hole with some debris around it. So this sets a very interesting stage for a, if you like, entire rejuvenation of the system with additional multi-messenger emission powered by the spin energy of the black hole and released largely, but not exclusively, through the torus. So one of the things that the black hole will do in its lowest energy state is to support an open magnetic flux tube that is very baryon poor, that through frame dragging is happy to accelerate particles on their lowest energy Landau state and all this kind of radiative physics, then ultimately powering an ultra-relativistic jet that would dissipate in the GRB that you observe. from the geometry here, you can also appreciate that that fraction of spin energy is quite small, which is what we observe. Because, for instance, for long GRBs, we have a very accurate estimate of 9 × 10⁵ ergs true energy in gamma rays. That's a very small fraction, like 0.1% of the total spin energy of the black hole. So that's accounted for by geometry, but then most of the energy goes into the surrounding torus that will be sufficiently hot and become non-axis symmetric. So it has its own quadrupole mass moment and becomes luminous in gravitational waves, in fact, contributing the major cooling of the torus through gravitational wave emission. And that is responsible then for ultimately spinning down the black hole. You know, there's a friction between the two, just like the clutch of your car, between the engine and your wheels. And so this is actually operating then at finite efficiency, but still such, because the spin energy promised by Kerr black hole is so much larger than that you can normally get in a neutron star, that still at the end of the day, you get much more energy out of it than that a neutron star can give you. And here it's at 3.5%. So that's the descending branch, because as the black hole spins down, the innermost stable circular orbit expands. And then of course, the radius of the torus expands. So everything rotates slower and slower until of course the black hole spins just as fast as the torus, and then the whole thing self-destructs. So that will be then the end indeed of both gravitational wave emission and the GRB. And the total emission is about 2% in gravitational waves. And this is a lot more than in total electromagnetic radiation, including the kilonova. That's actually interesting and perhaps counterintuitive, right? Because normally in daily life, we think of electromagnetic radiation as being strong and gravitational interactions being weak. That's what you teach if you teach, you know, something atomic. And the first maybe, yes, question.
I'm a neutrino guy, so I have to put it in neutrinos, which is more like 10% of the Rust mass in the collapse for the two neutrons. In relation to talking about the production of the hypermassive neutron star. Yeah, that's correct. That's correct. So the 2.7, you have to subtract 10%, roughly on that. Yeah. This is amazingly gravitational radiation competitive.
That's correct. That's correct. Yeah. Okay. Neutrino emission from the hypermassive neutron star. Yeah, that's correct. For the torus, we did an asymptotic analysis. We find gravitational wave emission is dominant, neutrino emission is intermediate, and magnetic winds is the least from the torus. But what you're pointing out is an essential piece of the gap 1.7, that if you look at that energy emitted in neutrinos, then indeed you get something. You don't have the same ordering. Yeah, that's a very important point. Maybe we should highlight that in our further talk, because we are mainly focused on, of course, the black hole torus system.
Of course, we have a snowball's chance in hell of detecting the neutrinos.
Yeah. MEV is so difficult.
Whereas these are easy.
Yeah. Right. Yeah, thanks for pointing that out. I mean, in some sense, you feel you never have the complete story on the energetics, even though the energetic, I think most would agree, is the most important, because that's the most reflective on, you know, do we have minimal feeling for the whole sequence because it's so complex? Yeah, that's a great point.
So Maurice, this is great. So it is time. So
yeah, I'm almost done. I'm almost done. Yeah, I'm almost done. But I wanted to give the one loop story of this saga. Okay, so we have great agreement between E&M and gravitational waves. This is an a posteriori check. I didn't put any PFA on this, but I think it's very satisfying. But it also shows that indeed this came from a double neutron star system, because the only alternative is neutron star black hole. But then of course you would never form a hypermassive neutron star. You would never have a delay in anything that we just talked about. So it cannot have been a double neutron star system. So that's an example of getting a nice result out of this gravitational wave. So I'll skip this. It's in our paper. You can look at this overview, basically energies and times on the merger sequence. And let me just conclude with 2 slides. So one question is, so firstly, what we did answer, we believe, is that is a question already posed in 2002 by Cutler and Thorne. At the time, as you can imagine, sort of a white paper, you know, what can we expect when LIGO is up and running? This was 2002. One of the comments they made was, you know, if we do get a signal from a GRB, then probably we should be able to say what was the central engine. So we claim that for 0817A, we now have the answer. We successfully are breaking the degeneracy between a neutron star and black hole. Now, what is next for 04? because it will be a little bit more sensitive, but a little bit is deceptive because a little bit is to the third power in volume, right? Because distance sensitivity and volume sensitivity, of course, introduces a cube. So if it's 30% more sensitive, that's very significant. So we'll see exactly, of course, how more sensitive it will be, but expect a factor of a few in event rates. So, okay, so we've seen mergers, but what about this particular idea of black hole spin down? That should be quite universal because black holes are very universal. And they may as well be central engines to core collapse supernovae, at least the ones of type BC that make long GRBs. And then you have an interesting question that fraction may be slightly more than those that successfully make GRBs, because you need a relatively long-lived central engine for a jet to successfully come out and break through the stellar envelope to be seen as a GRB. So this is speculation, so we'll see, but it certainly deserves to follow up on and probe nearby core collapse supernovae very seriously for their emission in gravitational waves. So ultimately, we might see something of E&M plus neutrinos, and internally maybe making a bit of a ketonova and the associated gravitational wave emission. And the signature will be very unambiguous, a descending chirp, not an ascending chirp. Okay, now, because I know time I'm spending now on the HPC part is a little bit short, but I would like to highlight one. I think what I hopefully did highlight is that we have an insatiable appetite for HPC. So we're always looking for what might be useful next. And recently we started a collaboration with Cerebras. I kind of just started this collaboration, emailing very innocently, what's your benchmark on FFT? Apparently that was a very non-trivial question. So that triggered a new collaboration, and we are now working on it because it's a very interesting architecture, apart from the fact that it's an amazing piece of engineering, you know, in terms of technology, thermals, and actually making chips as big as they do with sufficient yield. I don't know how they do that, but somehow they manage. But it's a very clean topology or architecture because everything is idealized to homogeneity. It's in some sense deceptively simply 850,000 processors on one wafer, each of them with its own little local memory and a individual router for communication with nearest neighbors. But many problems in HPC, so this is designed for AI and machine learning, which it does very well. Many problems in HPC are non-local. Take FFT, take match filtering. And people tell me that in some machine learning algorithms, there is also potentially non-locality. So how do you harmonize non-locality and something that is inherently local, but then scaled up to a large size? So that's a very interesting topological question. So we are collaborating on that. So when we are ready, we will hopefully be able to say more. So on that note, I think I should thank the audience. Thanks.
You can put a video on so people can see us on Zoom.
Yeah, go ahead.
So questions.
Yeah.
Is there any type of Grinnell or Huygens or Rayleigh kind of lens criterion that permits you from ruling out the possibility of the system that we're observing being more than just two neutrons, but like, because I guess like you had on slide 48, like it's
Let me see.
by a factor of 4 for a hyperneutron. So like you have like 4 hyperneutrons kind of producing the same event.
Neutron stars, right? Neutron stars. Well, you start with a binary. We know it's a binary. I mean, you have triple systems in astronomy. That's correct. But they would look quite differently. And one of them probably would have an orbital motion that would be too low to detect. So what we really detect according to this single chirp is just 2 stars merging. Now, 2 stars merging will make one object. You have to be a little bit careful. So you're touching upon a very interesting point if you translate this to a core collapse event. Naively, you think core collapse at the cartoon level, oh, something in the core that collapses to something compact, right? So there are propositions where they say, well, maybe it's too angular momentum rich, and maybe temporarily you might form a binary in a core collapse event with maybe a little bit of ascending chirp, or maybe not, depending on the mass transfer, and then make a single object. So indirectly, you're touching upon a very important point that may play out in the near future. But for this event, it seems pretty clear, the picture.
In fact, there's a lot of great astrophysics here. And in fact, Maurice will give another talk tomorrow, right, George? So can you, this will be at CAS, right? Yeah.
Room 383 on the third floor of the CERT building. You know where that is?
Yeah, so these are that's CAS,
It's
right?
a building that's immediately east of the Princeton.
Yes. Yeah. So there'll be more discussions then. So any perhaps any more questions on the computational INC side of opportunities, challenges? Audience here.
Yeah, my question is, how does this compare to the ADS CFT?
Well, this is in some sense, unless you want to talk about the fundamentals of gravity, all of this is classical physics, right? There's no, at the microphysical level, we are not saying anything new here.
Nothing relativistic?
No, but that's not new. If you ask about ASCFT, something like that, that might play out in something like late-time cosmology, and of course also very early cosmology, but that's observationally less accessible. So in late-time cosmology, you might ask, is there any role, say, in the H-0 tension problem? But even then, it's not so clear. But anyway, for this talk, we are encountering through this advanced observatory just an amazing combination of very different branches of physics, of which many, not all, but like the R processes, not totally satisfactorily quantified in terms of cross sections and so on. I mean, George knows much more about this probably. So, but those are not really the questions that would be sort of, the modern latest questions about, do we actually understand the space-time we live in? No, that's not relevant here.
Great, very fascinating story. So to be continued tomorrow. So at lunchtime, noon at CAS.
There is a chat. Maybe that means there is a question. Let me check.
No, this is
okay. Yeah.
Good. Well, thanks so much, Maurice.
Yeah, you're welcome.
Thanks for this.
Yeah, and thanks for
I don't know.
listening.
Will Gert take you over there or?
Yeah, I will certainly ask him.
Yeah,